something this rare, this unlikely, it's probably more likely that the true proportion of homes heated by oil is less than a fifth. That's the more likely scenario, or at least that's what our decision will be. We probably didn't observe something this rare. Probably the proportion is just not 0.2. It's something less than 0.2. So framing that in the conclusion, we always compare the p-value to alpha, the level of significance. Those are the only two things we compare. We don't compare the p-value to the test statistic. We don't compare the test statistic to alpha. We don't compare any other combination of things. It's only the p-value versus alpha, the level of significance. So in this case, 0.01, pretty obvious here the p-value is less than alpha. So we have a really small p-value, an unusually small p-value. So what that means is what we've observed is unusual. Since what we've observed is unusual, that means we need to reject the null hypothesis. Our initial guess no longer makes sense in light of this evidence, what we've observed in our sample. So if we reject the null hypothesis, then that means we support the alternative. And again, we frame our conclusions in terms of the alternative hypothesis. So in this case, at the 1% level, the data do support HA. The data do support that P is less than 0.2. So if we go back to the problem, it says, do we have reason to believe that less than 1/5 of homes are heated by oil? So we can just take that sentence and put that right into our conclusion. So the data do support that less than 1/5 of homes and we'll add in this certain city, we need to be specific, are heated by oil. Okay, so at the 1% level, the data do support that less than 1/5 of homes in this certain city are heated by oil. What we've observed was very unusual if the null hypothesis were true. So again, rather than believing that the null hypothesis actually is true and that we observed something very unlikely, it's more likely that the alternative hypothesis is true. We cannot say, however, that the alternative is true. We cannot say in other cases that the null hypothesis is true. Okay, the reason being, the only way to know the exact value of a parameter is to what? We have to have the whole population. We will never have the whole population. We will never survey every single home in the city to see if they're heated by oil. Okay, even if we could go to every city, doesn't mean every house is occupied. It doesn't mean we get information from every house. Okay, so we will never know exactly what this parameter is equal to. So we can never say that this is true. We can't say it's false. We can only choose one to support with some level of significance, meaning some sort of certainty that we're right, understanding there's a chance that we're wrong. We're working with imperfect data. Okay. This table on page 7, this was for example 1, that thought experiment where we were thinking about when would we call a coin unfair. So if we had 10 heads and 10 tails, its p-value is 58%. So very likely to see 10 heads or more if the coin is fair. So if that's what we've observed, we would just go ahead and say, yeah, the coin's probably fair. That seems reasonable. If the coin was fair, the probability of seeing 20 heads or more again, this was out of 20 flips, is really small. Okay, it could happen. It is possible to get 20 heads in a row. But what we're saying now is, if we imagine alpha is, say, 5%, we didn't choose one for that example. Well, this p-value, the probability of seeing what we've seen, if the coin is fair, is a lot smaller than alpha. So what we would say here is, we didn't actually observe 20 heads with a fair coin. What's more likely is that the coin is unfair. Doesn't mean that's the right decision, but that's how this process works. The p-value is less than alpha. We're going to support the alternative hypothesis that said the coin is not fair. Okay. So this also reflects that sometimes our decision will be wrong. It is possible to get 20 heads with a fair coin. It's just unlikely. So when we make these decisions and these hypothesis tests, some percentage of the time, we will just observe unlikely events. If they're unlikely enough, such that the probability of seeing that is less than whatever the level of significance was, we're just going to say, no, I didn't actually observe something rare. Some alternative hypothesis is actually the case. And sometimes that'll be right, and sometimes that'll be wrong. Okay, page 8, just a summary of the hypothesis test for proportions. I just try to condense everything, sort of hit the main points. So this is certainly something to read through, make sure it makes sense. If anything doesn't make sense, then you need to ask. Send me an email, ask during review, whatever. Okay. I don't know, certainly one of the most important things from that summary is the last bullet point. We have to remember in all of these problems and everything that we do, we're only working with one random sample. Okay? If we created that sample appropriately, if it's a large, properly gathered random sample, then we should do the right thing. We should make the right decision, but we could be wrong. Okay? So when we create our confidence intervals, we're making a conclusion from sample information, imperfect information. We don't have the whole population. So that's always something we have to keep in mind. That was the end of proportions. So now we know two ways to estimate the population P, the population proportion P. We can do a confidence interval that gives us a range of values, or we can do a hypothesis test. So that tells us whether or not the true proportion is equal to some value. Excuse me. So now we'll do the same thing for means. So now our parameter of interest is mu, before it was p. So it's going to be one of those two parameters. So when we look at our hypotheses, they use mu, not p. If you're working with continuous data, if you're interested in estimating a mean, then your hypotheses need to have mu. If your data are binary, yeses and nos, that means you're interested in estimating a proportion p, so p would appear in your hypotheses. This mu 0, that's the number. Okay, just like before, that's the value that you think the mean is equal to. So with proportions, that had to be something between 0 and 1. And it was typically more in the middle, like nearish 0.5. Doesn't have to be 0.5, but most of the ones that we used were in the middle, not at the ends. With means, in general, this can be any number, negative infinity to positive infinity, but the numbers you'll see depend on the context of the problem. If we're measuring heights, we're not going to think that the mean is negative infinity. It'll be something between, 4 feet and 8 feet. Those would all be likely values. Okay, it's not going to be 0, it's not going to be 1,000,000. It will be restricted because we're interested in measuring heights. So that will determine the values, historical experience, or random guesses or some other method will help you generate that value of what you think mu is. Here's the theoretical stuff. Again, I don't want you to get too lost in the weeds here. What we have to remember, though, is when we're working with means, we're no longer in the normal distribution. What that means for us is when we look at things like a test statistic, our test statistic is coming from the t-distribution, not the normal distribution. So with proportions, if we saw test statistics of, say, 3 or -3, we know from the empirical rule that that means that's unusual. In students' t-distribution, that's what we've called a fatter distribution. Okay, there's more data in the tails. So the result of that is, in some of these t-distributions, having a test statistic of 3 or -3 is not necessarily unusual. You need to be even further out to be unusual. So we won't interpret the student t test statistics, but the good news is we still get a p-value, and the p-value interpretation is the same, no matter if you're doing proportions or means. It's all the same. So the new function we'll use is the t-test. For confidence intervals, we had t-interval. Now we have t-test for the hypothesis test. And again, anytime you see t, that's generally telling you that you're interested in analyzing means. Okay, we'll skip example 6 for a moment. We'll come back to it if we have the time. It's just sort of a tricky problem. So example 7, a manufacturer produces television tubes, and it is known that the tubes have a mean life of 1,200 hours. So lots of information in this first sentence. We're producing television tubes, okay. The tubes have a mean life of 1,200 hours. So we see the word mean, so that's telling us this is not a proportion problem. We're going to be doing something with mu. We're interested in a population mean. So we also are told that it's known that the mean life is 1,200 hours. So we have some reason to believe that mu could be 1,200. A new process is being tested. They've randomly sampled 100 tubes, so that's n, created by the new process, and they found that the sample mean life, so there you go, you see means again. So sample mean, that's x bar, that's 1,265 hours. I guess I should specify that that was 1,200 hours for the mean. And the sample standard deviation, so that's S, is 100 hours. At the 1% level, so there's alpha, does the new process produce TV tubes with a longer average life? So what we're trying to show, has the mean increased? Is it longer than 1,200 hours? Since we have an alpha, a level of significance, that's telling us that these are our hypotheses. Again, the null hypothesis is always the equals. They'll have the same number, and they'll be the same parameter. So you'll never see a mu and a p together. It's either one or the other. You'll also never put an x bar here if you're estimating means. Okay. The purpose of a hypothesis test is to estimate a parameter. By the definition, a parameter is unknown. Well, x bar, the sample mean, is not unknown. We know what it is. We have a sample. We computed it. So we don't need to test what it could be equal to. We've already calculated it. So we never put statistics such as x bar or p hat or for that matter S, in the hypothesis. They're always parameters. Okay, so we are estimating a mean. We're measuring life and hours of TV tubes. That's continuous. So we're going to use the t-test. So a new function, but the use and interpretation stays the same. So we're going to input some stats. We have the statistics. We think that the average life is 1200. From our sample we had 1265. The standard deviation was 100 and the sample size was 100. And we think that the new process may be better. So we think the mean has gone up. So we calculate. So here's what we see. So there's our test statistic. Again, with means, we won't really interpret this. It has the same interpretation in the sense that this is saying if the null hypothesis were true, then what we've observed is 6.5 standard